Hi everyone, my name is Sara Webb and thank you so much for inviting me to give this talk at this symposium. I am incredibly excited to start off this week with why machine learning is incredible and why we as astronomers probably need to use it in the future. So I am at Swinburne University of Technology and I'm also on the Slack. So if anyone would like to contact me throughout the symposium or afterwards, please feel free to do so on the Slack or my email address, which will be at the end. So thank you so much to the SOC for inviting me to do a brief introduction to everybody. And now when I submitted what my title was going to be, I called it the tutorial for the broader community, mainly because I had actually just come out of surgery, was laying in a hospital bed with a little bit of painkillers in my system and not really thinking straight. And if I had have rewritten the title with my normal head on, I would have called it Machine Learning and How to Use It as Your Research Superpower. Because machine learning really is that. It allows us to do so many more things with the data than we could otherwise do. And as astronomers, everything we know is changing. But before we get into that, I'd like to acknowledge the traditional owners of the land which I live and work on, the Wurundjeri people of the East Kulin Nation, and pay my respects to their elders, past, present, and emerging. So, as I said, astronomy is changing. It is completely different to how it was 20, 50, 100 years ago. And it's constantly changing and it's evolving so quickly that for us to keep up, we really need to be tricky and clever with the methods that we use. Gone are the days of physically observing and manually analyzing data. This was the golden days where what you were working with really was tangible. Sure, you couldn't go and touch a star or a galaxy, but you could see it with your eyes, you could work with your hands on that data. There was not enough data to overwhelm you, maybe for a short period of time, but it wasn't like we were gathering an insane amount of data that was incomprehensible. However, as technology got better and as our knowledge grew, we started to realize that there was a lot out there for us to try analyze, and moving away from doing it manually was going to require some shift in our thinking and the way that we solidify our methods as well, and how we pass that knowledge down to new generations of astronomers. And that has been changing so quickly for the last 100 years. The way that we do astronomy has never quite been the same. This is really tricky and challenging because we don't know how this is going to change the way that we do astronomy or the way that we think about astronomy, which is something that I explore now in my new research. But for now, we'll keep it light. The fact that we have a lot of data. We are entering an era where it's no longer a group of people working in a room trying to solve a problem. We are now hundreds of people working in rooms all over the globe trying to solve problems. And the way we do this is really incredible because everybody needs to work collaboratively on the same sets of data. Now, we're heading to an era where there's an incomprehensible amount of data. This is, of course, the Hubble Deep Field, where almost every single spot, bar one, is a galaxy. If you are a galactic astronomer trying to understand morphology, this is amazing. This is your bread and butter, but this is just one piece of the sky. If we are to search and to try understand holistically the universe and whatever astrophysics we are trying to understand from it, there is a lot out there that we now need to analyze. And I think the perfect example is now going to James Webb, where we now, from one image, have the most distant galaxies that we have ever seen, ever taken data of. And again, just one image of one very tiny patch of sky. When we want to move to an era of not just analyzing one or two sources, but multiple statistical studies of the universe as a whole, we need to work with our data really creatively and efficiently. And going one by one through image with actual image inspection with our own two eyes to pick sources which might be interesting really isn't what we do anymore. We rely on machines and algorithms to do it for us, whether it be machine learning or not. And this is really interesting because not a lot of professions can say that they rely wholly on algorithms to determine what is interesting and not for them. So Again, we are now coming up to an era where we have the most remarkable data. These are just some of my favorites. Obviously, the James Webb Space Telescope, the TESS telescope, who is just receiving an incredible amount of data every single day across so many sources that we need to get smart with the way that we use it. The same with the Vera Rubin Observatory and, of course, the LSST survey, which will be occurring. All of a sudden, we need to be able to prioritize what data we want to look at. We can't just cherry pick as we go along and explore. And this is really interesting because how do you know what you want to look for? Some people might know what they want to look for. And if you do, I am very envious and very jealous, because in my past work, we were working with a lot of unknowns in what we were searching for. And this can be really perfect for machine learning algorithms to come in. But even if you do know what you're looking for, you do know that explicit thing you want to find, machine learning algorithms can make your job a hell of a lot easier than you manually searching algorithmically for things. So I'd like to start off by really summarizing that some problems are easier to solve than others. We all know this. We've all had very hard and very simple problems that we can solve. However, not every problem requires machine learning, whether it be easy or hard. We need to consider how we are using machine learning really holistically and really in-depthly into what is our exact problem. Not one algorithm will ever fit any range of solutions. Sure, we can tailor them, but we need to be pretty considerate and pretty thoughtful with what problems we are choosing to tackle. So keep that in mind, because as the theme of this whole conference is, the possible pitfalls of machine learning, this is one where we try attack every single problem with machine learning, and sometimes we don't need to. So I think a good example of this is when we're looking at traditional observational data. I'm an observational astronomer, so I'm sorry, I will go back to my roots and my biases of working with image data. And say we want to do something like look for appearing or disappearing sources. Maybe we are looking for supernovae or stars that have collapsed into black holes. We can dream. So what do we want to do with this data? And really, we want to make a list and compare it to another list. Maybe take one epoch, make a list of sources, take another epoch, compare those two lists. This is something that can be done pretty trivially, like with some algorithms. You can compare two lists pretty simply. You can compile your lists. Of course, all the methods into how you want to compile them are quite specific to your niche. But this is something that we can do without machine learning, right? However, we might want to do it a little bit differently. Instead of making lists with source extracting, we might want to actually use the images themselves, subtract two epochs and get a residual. And maybe we only have one list that now we need to work with. So both of these things that we can do without physically introducing machine learning. However, we could think about how we might want to use machine learning to make our lives simpler. And this could be, once we have our list of sources, how do we group them together? How do we identify what might be more interesting or more meaningful than others? But for the actual original task, it's maybe not something we need to tackle with machine learning quite yet. Something else though would be, maybe we are now looking for transit sources. We're looking for planets, maybe we're looking for primordial black holes, whatever it might be. We're looking for a change in the light curve. And for things like this, when we're looking for exoplanets, it's a predictable change in the light curve. And we can, of course, use traditional models and analytical filtering over our data to try present us with the data that fits those models, fits that algorithm to say this might be the dip that you're looking for. But we've shown that this isn't always the case, because some things are surprising. We can't model absolutely everything. And some of our standard modeling, say whether it's for a passing exoplanet or a flaring star, is only applicable for certain scenarios, and ones that don't allow ambiguity in them, ones that are very well understood. What could be different is using machine learning to break down features that these models never could. They weren't designed to do so. And we've seen it from Hoffman et al., a great example of how do we break down different features to be able to identify if there is a transit occurring in data such as TESS. And again, this can be applied very widely, but it's one example of when machine learning might be the right time to use it. It might make our job a bit easier, but allow us to look for things that we otherwise would not consider. So that brings me to my first question for you. When you are considering, you have a lot of data, you are ready to go, pumped up, you want to work on a project, the first thing you should ask yourself is, do you know what you're looking for? And I'm sure a lot of you just nodded and went, yeah, of course I know what I'm looking for. That is excellent. You have ticked one box. But for those of you who said, actually, no, I don't really know what I'm looking for, I'm curious about a heap of different things, or maybe my work is not well understood yet, that is okay too. But we do need to answer the question first, because this might determine what type of algorithms and what type of methods we want to use. So if you answered yes, congratulations, you have a solid understanding of exactly what you might be looking for. And this is something where supervised machine learning could be really, really useful and beneficial to your work. So the perks of using supervised machine learning is that we have a known set of data. So supervised means that we have trained some algorithm based on our prior knowns. So some more things to consider is you might know what you're looking for, but how many examples of pre-known things that you're looking for do you have? If it's one or two, this is not enough to do supervised machine learning. Again, you are then pigeonholing yourself into a very specific set of examples. So we need to first of all categorize how many examples, how much pre-known data do we have, or how many expected modeling data do we have? How can we build up our training set? We then need to move on to consider, from the data that we do have, the known data, what features do we want to use? Do we manually want to pick what features are important to us with the data? Because, we are all experts in our respective fields, and there are certain things that are more meaningful than others when we're working with data that might tell you what you need to know. So do you want to pick the features, or would you like to have the machine learning algorithm pick them for you? Because equally, as we know what is important in our data, there are a lot of things that happen in the data that are intrinsic to data that we visually do not see and do not physically identify as a feature. So the perfect example for this is when we use every single pixel when we're trying to do something like a convolutional neural network. When we look at an image, our brain doesn't look at every single pixel and calculate the different distributions of these pixels along the image to make up what it is. We are looking at the image holistically. And sure, we might zoom into a range of pixels that look more interesting than others, but we are not doing that mental math on every single pixel. And maybe there's a relationship between that could be, hidden to our interpretation of the image, but meaningful when we are using supervised learning. So these are things that we need to consider. So some examples of what would be absolutely ideal for some supervised learning is when we're looking for really specific objects or events. So some examples here is galaxy mergers or interacting galaxies. Maybe we have a whole sky survey. We want to pull out every single interacting galaxy we can find. To do so, we don't want to manually sit there and pick them out. That would take the rest of our life. So we're going to take some examples like this beautiful example we have here from a Hubble image, and we're going to train on them. Once you have a decent number of set of what they could possibly look like, then we can pick our features, or we can let the machine do it for us and we can train on it. It's something that is very identifiable both by our human eye and for a computational program to figure out as well. We could also look for something like what I've got on the bottom, galaxies that dip out past a certain point of dropout for emission. And this is something where we have data over a multitude of, in this case, different filters. This could also be true for transient astronomy where we have it over time, but we have multiple different intersections of this data that we want to analyze and evaluate. And this is also something that we could break down into a supervised problem. Another example I have here is, of course, a classic color magnitude diagram where very, very distinctly, if you're mapping stars or galaxies, whatever it might be, they do pop out in what seems to be very localized regions for different sources to lay. And this is a perfect example of, we know exactly where those sources might want to sit. Say we're looking for B-type stars. We can use all of that information to then build some constraints to supervise if we're getting incoming data. Does it fit this? Does it not? I end on this example though, because this is another one that could be overkill with machine learning, depending on what we're using it for. So it's another problem where this here manually, when we color them, we could maybe draw some manual bounds algorithmically in a program, a couple lines of code saying if you are between X and Y, you are this. So we need to think about if it's worth using things like this with machine learning. And I think there's some really, really interesting cases for yes, we can. So if you answered no, we don't know what we are looking for, that is totally okay, because that was my entire PhD thesis. So I'm very glad to make some friends with the same ideas. So that is okay. You might not be able to use supervised learning because you don't have a good understanding of exactly what you're looking for. So it's hard to train an algorithm to find that for you. However, things that are unexpected are excellent for unsupervised machine learning methods. And these might actually help you discover something new or discover more of what you were looking for. So some things to consider when we're using unsupervised machine learning is what makes a source or an object anomalous or different from the majority of the data. So this is applicable for any amounts of data that you might be working with. What makes it different and what makes it special. So I worked a lot with light curves. So in light curves, I was looking for things that went against the trend. Most stars don't change that much dramatically over short periods of time. So I was looking for anything that changed dramatically over a short period of time. I didn't know exactly what that would look like, but I knew that was going to be a feature that was going to be important. So then this leads in nicely to then we need to ask what features of the data might help us identify an anomalous object, because not all features will do that. So for my light curve example of I was looking for things that changed rapidly over time, if I was using a feature that took in a median value for my light curve over a very large boxed window, maybe it was an hour it took in an averaging. Something that's changing very rapidly within minutes wouldn't change the average of that hour-long box window very much. So a feature like that probably wouldn't be useful for me. So this is when we need to consider what features will be useful, and maybe using a smaller sliding box window, medians and things like that would come in handy, or Fourier transforms. So it's about thinking a little bit trickily, thinking outside the box for what features might be used. So what are some examples of things that you might not know you're looking for? And I think the ideal example is transients. Transient astronomy is an incredible field, and I say that wholeheartedly biased because I am a transient astronomer, but the amount of things that we find and we're not looking for them is remarkable. The universe is very dynamic. There is so much going on that it is impossible for us to predict or model every single type of event or interaction that can happen in the universe. And these are just some of my favorite serendipitous discoveries, things that we didn't know we were really looking for until we found them. And of course, gamma ray bursts from out of space. We all know the story of gamma ray satellites going up for Earth observation, really, to analyze were any cheeky nuclear tests happening in our atmosphere. Could we detect gamma ray bursts from that? And all of a sudden, we started detecting a range of gamma ray bursts that were coming from very, very, very distant places and galaxies. And now we better understand them to have two populations. We get our long and our short gamma ray bursts, but it's things that we otherwise wouldn't have seen without sending up a satellite to do a different job in the first place. Something that we didn't expect and could only really understand after getting the first data and computing in our minds what sources astrophysically could that have come from. We also get things like X-ray bursts, fast radio bursts, and pulsars. So all of these things discovered serendipitously, again, in data. So data streams that was being collected for other reasons, for other science, and these things popped out at us. And it's something that back in the day, before machine learning, if you had an algorithm programmed to look for one very specific type of event or source within your data, things like this might have been missed. And it was that human interaction, that human foresight and identification that led us to understand what these things are and that they are entirely new areas of astrophysics for us to explore. So I bring these up because I think it's really important when we think ahead to very large surveys, very large amounts of data that we don't want to miss having that human interaction with the data. We don't want to miss something because we programmed an algorithm so perfectly to do one or two really specific jobs that some of the data literally falls through the cracks because it was not designed for that. And I think some of the most incredible things that we've found in astrophysics are from these discoveries with human hands, human eyes. So that's something to think about. And I think unsupervised learning works very well for this because you are fed a plethora of unknown things that, depending on what you're using, when we'll get to an example later on, really do check those boxes for you. You can then dive through the data based on what the algorithm has spat out to say it is anomalous or not, and then evaluate with your own eyes what that is. It's not giving it a predetermined label or grouping. And I think that's really powerful. So let's start off with supervised machine learning. Let's dive a little bit into what exactly it is, and we'll do a little example together through our presentation. And then, of course, throughout this entire thing, I have links to different GitHub notebooks from either myself or collaborators where you can go and play with real data, play with these algorithms yourself, and adapt them to the work that you might be doing if that is of interest. So supervised machine learning, it comes in two flavors, either chocolate or vanilla, whatever flavors you like to call it. It is either classification or regression. So let's start with classification first. So really, does your problem require a yes or no solution? Can you bin it in a certain box? Can you separate them clearly? And, can you classify the results in really discrete ways? So an example of this is it a koala, a kangaroo, or an emu? I had to put a little bit of Australiana in the talk for you guys. So say we have an algorithm. We have a heap of Australian animal pictures and we want to classify them into either koala, kangaroo, or emu. We know that they are their discrete ranges. We know that we're not going to get a kangaroo/emu hybrid. I hope not, that would be terrifying, but we know that that's not going to happen. We're very confident that the images we feed are either going to be one of these three things. So this is a perfect example where we can train an algorithm knowing these three things to give us a yes or no answer. Is it a koala? Yes or no. Is it a kangaroo? Yes or no, rather than a discrete, a non-discrete range. So then we move across to regression. So this is where our problem might require a continuous output. So this might be trying to input some data and guess a person's age or a person's height or the number of lollies that are in a bag. It's something that is on a continuous range. It isn't just a yes or no answer. We need multiple solutions and multiple possibilities for what it could be. And really, it's kind of, we can think of it as at least my brain thinks of it kind of like a probability. Well, what is the probability that it is something along this continuous range? And so just an example is the age. Are you between 0 and 99? And can we guesstimate what direct age in there you are? So if you were going to use classification, you have things like random forest, decision trees, and support vector machines at your arsenal to use. And these are brilliant for being able to train on a known subset of labeled data, known data, and then you can feed in unknown data to get those very, very black and white, yes or no, or a categorized answer. Works very well. For regression, these are things where we look to use algorithms that can offer us linear regression, regression trees, or Bayesian linear regression, or polynomial linear regression as well. So this is really algorithms that give us that output along a continuous line, a continuous spectrum of what it might be. And again, can be trained to your labeled data, but it's not black and white. It's not a classification problem. So we've got advantages and disadvantages to supervised machine learning as a whole. As does everything in the world, we have advantages and disadvantages. So let's start with the pros. So supervised machine learning is really easy to break down a problem in your training set. So that example of koala, kangaroo, or emu, three different things that we can break down quite easily. And our training set is not overly complicated. It really is three labels with data. So It works really well if you have distinct and exact classes of data. Again, our koala, kangaroo, and emu works very well. And it is useful in a vast range of problems. So it really is not defined to one type of set of problem. If you have groups or categories, you can use supervised machine learning. However, we do have some disadvantages. So machine learning, supervised machine learning, I should say, is not suitable for really complex tasks with lots of unknowns. So you can't use a classification or a regression model for something that has an exorbitant amount of unknowns. For many unknowns in the data, it doesn't work very well. And it could end up actually making your data and your solution more non-trivial than you really wanted it to be. It can really complicate things. So that's one consideration, is if your task is very, very complicated and you can't separate what you're looking for in really, great training labels and sets, maybe is this the task for you? We can also not predict outputs. We cannot predict outputs for data that it was not trained on. So my kangaroo, emu, koala algorithm works excellent for those three things. If I chuck a dolphin in there, it doesn't know what to do. And it can do its best to try put it in some category, but it was not trained on that. It can't figure out that that is a completely different thing. So that's something to consider. Another thing is that training is really computationally expensive. When you have a very complex model that you've worked on, to train it with the right amount of labeled data that you need can take lots of time and require lots of resources, and can require things such as supercomputers to really do effectively. It's you don't want to just run it on your CPU on your laptop, because it might take a ridiculous amount of time. So that's something to consider as well. So let's chuck ourselves into a real world problem of where supervised machine learning was an excellent solution and an excellent tool. So we're going to look now to Good et al. 2022, and all of the different links will be on the bottom of the page. You can go direct to the data and to the notebook where we actually do this work. So for some context, this work was designed around the Deeper, Wider, Faster program. This is a program where we are taking continuous images using CTIO DECCAM imager of the sky every 20 seconds, and we're looking for new and exciting transients. So things like this have a silly amount of data coming in every single minute. And we need to work really smart with that data, because there is not enough human power to visually look at every single source and determine is it interesting or not. And something that really hinders this work is the presence of bogus artifacts in our subtraction. So this, we do it via a difference imaging pipeline. We compare a new image to the past template and see if something has changed. So you either get real astrophysical sources of significance, or you get bogus sources or bogus subtractions. And a range of things can cause the bogus, and that is where it gets a little bit interesting. So it's something that we can break down though. So what we can do is we have really distinct categories. We know that we have several sets of different types of bogus things that can occur, and we have several sets of real astrophysical sources that will occur. Each is different, so each image is completely different to the other, which is really important. So we also have access to science template and subtraction images. So it's not just a subtraction image, we have the two prior images that we can train an algorithm on, because all of that information is really important when we're trying to figure out, is it a real or a bogus source? We just don't want to trust the subtraction alone, or in this case, we didn't. So we then needed to think, is it a regression problem? Because some things are more bogus than other things. Sure, we can label it black and white as either real or bogus. However, one example of what bogus might be, bogus, fantastic word, is a misalignment. So all of a sudden our images don't quite align and we get a little bit of a misalignment. So we get a negative residual in our subtraction. The source might still be very much real, very much there, and it is getting brighter from the template. So we do have a positive residual, but we get this weird negative ring around it. So this could be considered either real or bogus. There is not a clear consensus there, which I will actually touch on in a minute. So this is what we wanted to treat as a regression problem, not just classification, because we really wanted to put it on a line from 0% real to 100% real. What does our algorithm think it is? How bogus does it really think something is if it's labeling it as bogus? Because we want to look at everything that could be interesting. So it also, conversely, could be a classification problem. Maybe we don't care about how bogus something is. Maybe we only really want real bogus, no in-betweens, no gray area. And that is totally okay too. We can do both of these. We can do both regression and classification in the type of machine learning that we used for this problem. So again, these are just things that you need to consider when you are working with your data, is what answers do you want to get out of it? And really tailor your solution, or sorry, your algorithms to get you the answers that are best for you to work with. So the first step to any supervised problem is having your labeled data. And this was amazing because we had an enormous amount of data that we could get experts to label for us, including us as experts doing the labeling, but also additional people, which meant that we could get multiple labels for the same data. So we could do an overall consensus, which is important because when you're working in astrophysics, I do not need to tell all of you, but it's very rare that something is so legitimately one thing that you could take all the astronomers in the world and they would agree and concur that it is exactly the one thing. So especially when we're working with data like this, where there is a lot of gray area, some people can disagree, and that is totally fine. That is human nature. We all interpret data differently, and this is why it's quite important when you're thinking about labeling your data, who is doing the labeling and how many people are doing the labeling, because that can be really important. That could change your outcome of your machine learning if someone has labeled it to a different way that you might think or someone else might think. So for us, we labeled our data in really discrete categories. So it was either labeled as from nowhere, an asteroid, it was either galaxy light, so this was a source that was either within or nearby a galaxy, or it was a star, so a source that was pretty convincingly a star based on the fact of its point spread function. So these were our different labels. And we also, of course, had our bogus labels. So anything that didn't fit into those categories that looked a bit dodgy, it could have been things like misalignments, missing template images, cosmic rays, crosstalk, missing pixel channels, hot pixels, all of those things that are not astrophysical, that have made the data a certain way, we can label as bogus. So I mentioned about getting multiple people to label your data. And this is why I think this is one of the most fascinating things that came out of this work, is that all of our experts, all of these people who have spent literally hundreds to thousands of hours looking at data just like this, do not agree on what it is. And we can see here, we can break down that on bogus, most people really agree on what bogus is. It's pretty black and white. For agreeably real, though, this is where we get ambiguity. Need to stop saying that word. This is where we get gray area coming in. Because what we see is not everybody agrees on what type of source it is, or if it is even real. So this was really interesting to us because we kind of went in with the opinion or the forethought that everybody was going to agree on the exact same thing. We've all seen hundreds of thousands of these cutouts. How could we not agree? We all agree when we talk in consensus, but this is how we interpret data. This is really important because every human sees something a little bit different or interprets it with their prior knowledge a little bit differently. So what we were able to do is take the average. So we took the average value of if it was either real or bogus or the other subcategory. So this is something really interesting and maybe to consider when you are using labeled data. So this was the bogus. These are things that we would count as bogus. So you've seen the lovely real looking subtractions. These are things that we see as bogus. And now what is important and why we chose to use the science template and the subtraction images was because bogus things can appear in all of them. So things like crosstalk, cosmic rays, missing pixels, missing images, these things can occur both in the template and the science. It's not just a result of the subtraction of the two. So we really needed to label using all of them. And the one label that we would give would go across all three images. So the next thing we would do is compile them into our groups for either star, galaxy, artifact, asteroid, crosstalk, whatever groups you wanted to do, whatever groups we decided, whatever groups you decide when you do a similar problem, they are now your distinct buckets of what you're working with. And depending on how many things you have, you might want to consider data augmentation. So this might be, we have 100 really good examples, but our algorithm would probably work better if we had 1,000 really good examples. Now, we don't want to just make up data because that's never good. Put that on a t-shirt and quote me. We want to use the data that we have. And so what we can do is maybe we can rotate it, we can flip it, we can zoom in, we can zoom out, but all using that previously labeled data to build up our training set. So that's something to consider as well. So we can then compile all of these different categories really down into this classification problem of, is it real or is it bogus? And we can give it either a 0 or a 1. So it is, if it's real, it's a 1. If it's bogus, it's a 0. And we can use this to then train our algorithm that we chose. So before we do any training though, we first of all need to normalize our data. And the way that Good chose to do this was to normalize it and then store it in arrays and then be fed back into the algorithm. So very important. We didn't want to just go with all the raw data. So we chose to use a deep convolutional neural network. And we chose to do this for a couple of reasons, but mainly we wanted the features to be picked for us. We didn't want to go through manually picking what features there were. Good decided that this was going to be the best approach, and it worked really lovely. So we first of all do a convolution layer where basically you are grabbing a feature map from your image, whether it be each pixel, each size, you get to really decide on what your feature map will be. You can then do dimensionality reduction. So we don't want to work with all of the different pixels that we have there. We want to reduce it down, and we can do that with pixel relationships or mapping relationships. And then we feed into the connected layers, which is where the learning happens, where we assign weights and biases. The computer does. We definitely do not do that manually. But this happens in the training. So you give it your training set, it knows the outcome it needs to get from the data and can adjust the algorithm to meet what you need. So all of this we decided to output as a neuron output in a regressive style. So we could have just had it, we could have added another step beyond this to give us either a black and white, real or bogus, but we wanted to keep that continuousness in there. We wanted to see what is more real, what is more bogus. So we decided that the output was going to be between 0 and 1. And you can think of this kind of like as a probability. 0 is 0% real. It's the worst of the worst, where, 1 is 100% likely real. It's the best. So this is how Good et al. Decided to output this in our program. But we can change the way that we output it. And if you would like to explore more, please, I really encourage you to go to both the robot paper, where our team fully describe the full method that you can read over, and then also the GitHub, where the robot pipeline is stored for examples and for playing around with the data yourself. Because if it's a similar problem or something that you're interested in learning, this is a really good way of getting that hands-on experience and working through it yourself. So we're then going to move to some unsupervised machine learning, and because it's from my work, you can probably tell I'm a bit biased. I think it's incredible. I think we can do so much with unsupervised machine learning. So one of the problems that I wanted to solve, again, was working with deeper, wider, faster data. So instead of working with image data, I was working with light curve data. And over the course of the program, the DWF program has accumulated an incredible amount of really fast cadenced light curves. And it really is a testament to this program that we have light curves with such fast cadence and such volume in different areas of the sky. So one problem we had was, how do we break down what we want to look for? we could have picked one thing that we were looking for and write an algorithm around it, a non-machine learning algorithm, to find exactly the one type of event or pattern that we were looking for. However, this would have limited us, and that works when you are trying to solve a very specific problem. For my research, though, we were trying to understand this transient universe as a whole, the transient sky as a whole, and look for things that might have been poorly understood or not understood within our data. So we really wanted to take the machine learning unsupervised approach to give us everything in our data that was anomalous, so we could then further analyze it. So just to reiterate kind of what I said before, was we could have picked to just use complex flares or flares in general, used the model of a flare and searched our data and found what we needed. However, this only works in very specific cases. The normal flare model would not have worked well for something like this. And it would have missed things like this. So maybe we're looking for variables, or maybe we wanted to see if there's any anomalies happening on a variable. There is not on this one, but a good case for you're really kind of picture holding yourself if you're using one searching algorithm, which is totally fine depending on the science you want to do. But for us, we wanted to keep it a bit more broad. And this was just an example of us using like a very fitted algorithm to identify and model flares, which only work on very certain cases, not on complex flares, not on very fast flares, and not on flares that have data gaps. So we wanted to just see what else there was. And of course, we don't know what we're looking for. We would love to find an unusual transient, any unusual transient. Maybe it's something that did not exist before. We have non-detections and something comes out of nowhere. So there was always the possibility of looking for something that we had no idea what we were looking for. Back to that serendipitous discovery idea of we wanted to just get the data that was most likely to have something interesting or anomalous in it so we could visually look at it. And this all maps really, really well back to the Vera Rubin Observatory and the LSST, which will be happening. We will have so much data that you can pick and choose what you want to look for, but we also want to use that data to find things that are unexpected. So before we dive into what we did, let's break down unsupervised machine learning a little bit further. So clustering. We have two different types of unsupervised learning, and clustering is the first. So we have many different types of clustering depending on your needs. So I've broken down the main ones here for everyone. So we can either have exclusive or overlapping clustering. So what this means is exclusive clustering is two things exist in feature space. They do not overlap. It's not a Venn diagram. It is two circles living their best lives, no overlapping happening. We then have overlapping clustering, where we then have these things that could occupy the same feature space. So maybe an example could be we have a cat and we have a dog. It is either a cat or a dog. It is not in the middle. And what would happen if we were using something that was looking for this exclusive clustering would assume this prior would assume that things do not exist in the middle. But we might have another example where we have things that can exist almost anywhere, maybe more so in a different cluster, but they could overlap, a bit like a Venn diagram, clusters that are not distinct. And this is where we can use like fuzzy clustering, something called fuzzy k-means, can help find things that belong to multiple clusters. We then have something called hierarchical clustering. Now, this is really interesting because it works either from the bottom up or the top down, and it's assuming that we have clusters that are very different to each other and that do not occupy the same type of feature space. So depending on what type of algorithm you were using, we can either go from top down or bottom up. So maybe we're starting assuming everything is separate and we're trying to find where they connect, where the clusters grow, or we can go top down, pretend that everything, or start with the understanding that everything is somehow connected and work our way down into separating them into smaller clusters. I really like this because it works quite well for really complex data sets that have a lot of different nuances in them. We can then go to probabilistic clustering, and this kind of works on a few of these different levels, but can give you likelihoods of what cluster it belongs to. So it's neither black and white here or there. It can be, it can give you that kind of regressive understanding of it could belong to this cluster, but it could also belong to this cluster. And things like Gaussian mixture models are used for things like probabilistic clustering. We can then go to dimensionality reduction, where instead of clustering our data, we just want to understand it in less dimensions. So we can do this with principal component analysis. This is one of the best ways to take in a heap of your features of your data, or take in your data in general, and break it down into a more accessible, workable feature space. So we can reduce it into maybe a 2 or 3 dimensional components. And these things use linear transformations depending on what type of feature distance and space you're working in. We can then go to singular value decomposition, and this is using a matrix transformation to work on your reduction. So again, reducing from X amount of dimensions to a smaller amount to make it easier to work with the data or to visualize the data. We also have things like autoencoders, and this is to try reduce noise in data. So it can be used with neural nets, and really to get rid of the background noise and highlight and reduce the data down to only give you things that are most of importance within the data. So back to our real problem example, where we have all of my light curves, we have lots of different light curves, and we don't know what we want to look for. We just know we want to look for things that are rare, that are within them. So to do this, first of all, we had to grab features. It's not like a convolutional neural network where we can make the algorithm determine the features for us. We could have used something like that, but again, we're using unsupervised techniques. We didn't know what we were looking for. We didn't have labels. So we wanted to define the features that we use. And features are only limited by your imagination, by what you think could be a feature. Obviously, some features will work better than others, depending on the type of data that you are working with, but really, you can decide what you want to be a feature or what you don't want to be a feature. So some really common, really basic ones that still work really well are things like mean, median, modes, what is the moving average, what is the slope, what is the rate of change, things like this that are very easy to compute but are really meaningful when we start to do feature analysis. You could then get a little bit more complex, and maybe you're doing amplitude variability. You could be breaking it down into quartiles and using different features in the quartiles. Maybe you're doing Fourier analysis. Lots of different things that you can do. And there's some really, really great astrophysics papers that break down what features are best used for different tasks. And so the papers that I used for understanding what features might be best for me are Richards, Kim, Precara, and Kim Baylor-Jones and Stenson's et al. All of these papers tackle a slightly different problem within trying to break down a feature space of an object, and often over time series. And these were the ones that inspired our selection of 25 different features. And these are features that were used for both variability in stars, variability in quasars, for flare stars, for all sorts of things. So it was really a broad range to kind of give us a nice coverage of what could be important. And most of them can be derived using pre-programmed libraries, especially in Python. So there's the FEATS or the FATS Python packages, which have the majority of the features that astronomers use pre-programmed in. You just give them your data and away you go. It's very, very nice. Some other ones, especially the ones that you come up with yourself that might be meaningful to your data, you'll need to manually compute, but generally speaking, features are not crazy difficult to get out of your data. So the next problem is we have all of these great features that describe our data. What type of clustering do we want to use? Because again, the world is our oyster. We could use anything, but we needed to consider the problem holistically. So with our data, we did not expect that the clusters would be the same size. So we did not expect that 50% of the sky would be unchanging, 50% of the sky would change. That's not realistic to what happens in the sky. We knew that there was going to be a lot more variable stars there were, short duration flare stars. We knew that there was going to be a lot less, extragalactic things, or things that were below threshold and then come above threshold of detection. So a supernovae, for example, a lot less of them than anything else, if any. So we really needed to work with something that could handle the different densities of our expected clusters. And this is where you have to ask yourselves is, do you expect the different densities? In our case, we did. In some other cases, maybe you don't. So yes, we did. So we wanted to use a density-based clustering, but we also wanted to use it in a hierarchical system. So we wanted to use HDB scan, because what this did was separate data on different tiers as well as different densities, which worked quite nicely for our data. So to highlight, HDB scan kind of works like this. It takes all your data and it's working top down, where everything starts connected and we're trying to separate our different connections. And this is just a really nice one of the classic examples of how HDB scan can work, handling different clusters of different densities. And they're colored there in the different clusters that were identified by HDB scan in a dimensionality reduced space, so we can visually see it. And it works really well. So this is something we were really excited to try and use on our data. So to break it down, I wanted to first of all show a TSNE. So this is a dimensionality reduction plot of all of the 25 features we used, colored with the clusters that we found using HDB scan. So the axes are arbitrary. This is just a projection into 2D space, so our brains can conceive what is happening here. But our clusters are colored in distinct colors. So we have green, purple, black, and gray. Now, it is probably very, very obvious that the majority of this data is grey, and that grey data really is spread out. So what's really interesting about the TSNE is the way that it warps and contorts data to best represent the clusters that it's seeing. So all of that grey data is actually very closely related, very closely clustered in that feature space. And that grey data that we find is unchanging sources. So we were using light curves that were taken over the duration of a night, with maximum about maybe 2 hours of observing, so not an insane amount of time on the sky. And we were monitoring sources, mainly stellar sources. In this time, we do expect that most stellar sources and even extragalactic sources are going to be unchanging over this hour to 2 hour time period. And this is exactly what we see here with that grey grouping. We then also have two other groupings, which were green and purple. These were further broken down into variable stars or other changing types of stars. And the thing that is most interesting is actually not these clusters, but our unclusterable data. So data that was so distant from any of the other groups in feature space using our Euclidean distance that they were marked as unclustered. They didn't really belong anywhere. So what this is our anomalous data, the data that might be the most interesting because it is the most different. So I thought I would break down what this looks like when we actually kind of break it down into different groupings. This was from another data set, and if you want to check out the in-depth explanation and all of the different things, please have a look at my paper from 2021 on unsupervised machine learning for transient discovery. I think that was the title, something along those lines. You'll find it. And what we see here is really, really different types of sources, and they are grouped really, really nicely. So we obviously have in our group one steady sources, they're unchanging. We have a couple of examples of variable sources. So what we have in G2 and G6 is things that have variability. Now, G2 was true variable sources. These were from stellar sources with actual astrophysical variability. In G6, this variability was caused because of CCD dithering or near edge detections. So it was an artificial variation, and the machine learning, without, again, unsupervised, no labels, no input, figured out these patterns were very true to this one type of thing. So really, really interesting. We also had some other things. So we had clusters of things that were majority under the detection threshold. So this is really useful for if we're looking for things that have only just appeared, we can use this to solve that problem. In group 4 and group 5, we see things that happen because of dithering. So we dither at the beginning, we stare, and then we dither at the end. And what we see here is some sources that only appear in the first dither and then they fall away because they're not on any chip to get data. And we also see here some sources that are affected from the dithering. They stay on the chips, but their light source is altered because they're getting near the edge of chips. And those 5 points are unreliable. And they clustered beautifully. This is excellent for being able to clean up our data. We also had things like bad pixels or cosmic rays that just really were beyond the rest of the data, really nicely isolated. And then we had like other issues from like blended sources, bad pixel lines, things like that. All of them fell into groups that were very, very clearly related to themselves in that individual group. One thing that we were super excited to see, and this came from an unclusterable source, so things that didn't really fall into any of those previous categories, was a really fast flare event. So this, again, these are 20-second cadence images. So this flare happened within less than 3 minutes for it to rise and fall back down to its quiescent state. And it rose quite significantly from its magnitude values. When you convert that into flux, it's not trivial. It's a very, very awesome flare. And we found a few of these in our non-clusterable things. They weren't quite enough to form a cluster, but they were different enough from the rest of the data to be identified as anomalous. And this led us to want to work on our next problem. And this is where we move now to one of my 2022 papers, where we're looking at using unsupervised machine learning to find short duration flares. So what we did was we then applied this unsupervised machine learning. We'd done the proof of concept, tested it, determined what it was able to do. We then applied this to, I think it was something like 85,000 light curves in total. So we then applied these to the fields that were fairly galactic, still had a lot of stellar sources in them, to try see if we could find these ultra fast flaring sources. And we did. We found 97 different flares that occurred, and they occupy quite a really unique region of this particular phase space of flare duration versus the integrated flare energy. So how much energy the star is emitting just over that flare time. And all of ours are in those beautiful colored plots, colored dots that you see there, and they're colored according to how far off the galactic plane they are. And so we see that we kind of bridge this little gap between our known solar flares, so our own G-type star flares that we can study very well using our sun. They're very small flares, micro flares, not very intense, to the super flares that we see happening on other solar-like stars from the Kepler and the TESS surveys. So we almost bridge that little gap there, and we see these happening across majority of M dwarfs, which is absolutely expected based on M dwarf physics. We also see that they're more often occurring near the galactic plane, again to do with different density populations of stars within our galaxy and the type of stars distributed out from the galactic plane. But this was really, really awesome because we were able to use this machine learning that we really used for discovery and apply it to do physics. So this was really, really a great example of what machine learning can do and how machine learning can kind of delve you into areas that you might not have expected to work in. I definitely did not expect I was going to be writing a flare star physics paper at the beginning of this work, but I was very excited to do so from what we found using these methods. So to sum it up, this work used different types of feature extractions, HDB scan, principal components analysis, and TSNE. And all of these things are highlighted in my, my GitHub ML light curve clustering repository, where we've got some dummy, some example data and some step through notebooks that you can use to cluster, do PCA, have a look on a TSNE, and just play around with the data and things that you can copy and use exactly to your own data. So to wrap up, we've done 2 examples of either a machine learning that's supervised or a machine learning that is unsupervised. But if you were really, really keen to dabble in what it could do to your data, I wanted to give you a bit of a resource toolkit for what things to turn to when you were starting out or when you were stuck. The first one I wanted to highlight is Kaggle. So Kaggle courses are excellent short tutorials, and they're workable examples for you to build your data science and your machine learning skills as you go. And they're bite-sized chunks. You can do them. You don't have to dedicate a week. You can dedicate a couple of hours to do them. They're really, really excellent. There's also the Astro ML Python module. So it's built around using scikit-learn, AstroPy, Matplotlib, all of those good things that we already use, and highly recommend checking it out so you're not reinventing the wheel trying to write a machine learning algorithm from scratch when one that might be suitable could exist in this library for you. Also Coursera. So I know that most of us have been learning for a very, very long time, but it is always really good to kind of upskill what you know and what you can do. And most of what I would recommend on Coursera is actually data science courses. So optimizing how you're handling and how you're working with your data. And this will become really important when you're doing your feature analysis and things like that. But also just a really good place to turn to for examples that aren't necessarily astronomy based. So it can be really hard when we're working in astronomy and we might have a very specific niche problem that we want to try find an example exactly for that one problem. And in reality, that doesn't really exist. But lots of other problems and lots of other examples and solutions on other data do exist that we can apply to our own. Data is pretty transferable and so are your skills. So highly recommend Coursera. But the most important tool I think you can have in your toolkit as an astronomer is something called Astronomy. So this was developed by Lochner and Bassett, and you can read the full paper on the archive. But I'm going to give you a bit of a rundown about how powerful this tool is. So they have really created something that is for the full community of astronomers who are working with different types of data sets. And really, the most important thing about this tool is that you don't need to be a machine learning expert to use it. You don't need to have any of the background knowledge in a very specific machine learning niche to be able to find anomalies in your data. Machine learning is so powerful, especially unsupervised machine learning, in trying to identify things that are not like the others. It's like that play school game, which I realize if you're not from Australia, you might not get that reference. Forgive me. So it really, really is powerful, and it is a flexible framework for detecting anomalies in your astronomical data. So what it can do in the back end is use something like an isolation forest to identify the most anomalous sources within your data and present them to you. So you can visually work with your data in an interactive GUI. So you're hands-on back with your data again, analyzing it. It's not just numbers behind a terminal. And then you can then feed back in what you think about that data. Was it anomalous? Was it or not? And you can retrain the algorithm. You can also have a look at things using a TSNE, so that collapsible feature space that I mentioned before, where it is colored based on its anomaly score. So its anomaly score using the isolation forest and a few other things. So what you can see here is that you can go and select a point that by its color and by its location looks different to the others, and it will visually show you what that thing is, what that cutout is. Really, really handy for when you're working with image data to quickly find things that might be of interest. And I mean, the one thing I can think of is loading in some of the new James Webb Space Telescope photos, especially the deep fields, and just seeing what it thinks is anomalous. If you do it, please let me know. I think it would be amazing. But what you can also use it for is looking at time series data. So Michelle was very kind to help me kind of custom rig up my Astronomy to solve the problem I was doing. And now if you use the development branch of Astronomy, there are a few really amazing new features that you can play around with. But this is just an example of what you can do. So again, using unsupervised learning to give me the most anomalous things in my data. And then I could also use the TSNE to visually search around and see what was happening. It was incredibly powerful, a really powerful tool, something that, you know, again, you don't need to have this crazy amount of expert knowledge. You can just chuck in your data and have a play around. And it's a great way for you to kind of get used to and get familiar with using anomaly detection with unsupervised machine learning. So finally, I think after wrapping up, we need to consider to use machine learning holistically. So before you're diving into the hardcore programming, before you spend weeks, months, years, however long it might take to write the perfect machine learning algorithm, write out what your problem is in pseudocode and plan what you need to do for each stage. And then try reflect back to the problem that you're trying to solve and see if it's really answering that question that you're looking for. You also don't want to spend years writing a custom built machine learning algorithm using pre-existing code, program models, all of that good stuff. That has been done. A lot of problems are adaptable to code and to programs that have already been written for you. So use pre-existing code programming models to your advantage and collaborate across sub-disciplines. So you might go from transient astronomy to maybe like simulation modeling astronomy, things that, we're all working with different types of data. Our problems might be different, but we can use similar tools to solve them. And also look outside of astronomy. Again, Kaggle, have a look at some of the different Kaggle challenges and solutions that have been posted there for a range of different problems. A lot of them can be adaptable to you. And finally, have an open mind. It can take several models, iterations, algorithms to find the one that actually works for your problem and to give you the solution that you might need. So have an open mind and try a heap of different things before closing your mind completely to machine learning, which I doubt you'll do. You're here at a machine learning symposium, so hopefully your mind is already in love with it. So use it as your superpower. As I said at the beginning of my talk, data is changing and we're going to be relying on brokers to feed us what is interesting. And the best example of this is all the brokers that are being developed for the LSST server on the Vera Rubin telescope. There is going to be so much data that we are going to rely on brokers with machine learning algorithms built in their backend to deliver us data that might suit our science cases. And so this is where it really comes into its own and really will help us navigate our future as astronomers where we're not manually handling our data all of the time. And finally, work smarter, not harder. So some of the best things that helped me when I was learning my first machine learning project and wanted to learn a little bit more, dive in further, was a lecture from Rob Fergus that is online. I've attached the link there. The most amazing lecture to go through and just wrap your head around it. Something you can work through in your own time. Really, really incredible. There is also another incredible GitHub repo that I recommend by Tanud Askanini, who has put together machine learning for astronomy, a heap of different examples, working through a heap of different types of problems, but step by step and things that you can do, again, in short chunks. You don't need to dedicate very long time to learn. And of course, the Python Data Science Handbook, if you don't want to physically read the handbook, on GitHub, there are a range of examples, and data science is really important when doing machine learning. So in summary, thank you so much for listening to my talk. Again, if you're listening to this one, I'm recorded, but please come and ask me questions on the Slack, or you can email me at swim.edu.au. And I really hope that you enjoy the rest of the conference, and I cannot wait to see all of the other amazing talks. Thank you.